This section introduces us to the concept of work, and work is important because it relates to energy conservation. So right here we have delta E, the change in energy between the final and the initial, is equal to this thing called work. Now, since we haven't learned what potential energy is yet, we're only going to look at kinetic energy and work for right now. So our initial energy is just our kinetic energy. Our final energy is our final, and all I've done is rewrite this equation. All right, so let me just write down, this is also delta E equals W. Notice that these are all scalar equations, and this is one of the benefits of dealing with energy, because we don't have to deal with directions anymore. We don't have to deal with vector quantities. So what exactly is this work? Well, let's consider that we've got some box that we're moving, and we're applying some force to it, and we move it some distance, and we want to know how much work is done. Incidentally, looking at our equation for energy, that K initial plus W equals K final, we can see that the work is essentially the change in kinetic energy here. So if we apply some force over this distance, the work done in this case is just F times delta R, where I'm just dealing with the magnitudes. Now, if we apply twice as large a force and move it the same distance, we actually get 2F delta R, or twice the work. Now, obviously, if you're applying a force twice as large, this thing's going to speed up a lot faster, and it's going to take a lot less time. That doesn't matter in this case. What matters is how far that object has moved during the interval when the force is applied. So even though this object is moving faster, it took less time. The force is twice as large. Now, what do we do when we have a vector force and a vector displacement? In other words, it's not just moving along the x-axis or the y-axis. What it turns out is that we can break things up into components. So I can consider this force to be made up of a force in the y direction, a force in the x direction, and then I'm going to consider the motion to be the component of motion along the y-axis and the component of motion along the x-axis. So here we have the box with the force in the y component, and it's going to move a distance corresponding to this distance right here. And the work done in moving there is just equal to the y component of the force times how far it's moved in the y direction. Now, obviously, the box doesn't move in the y direction, but we're just for mathematical purposes considering that. Now let's apply the x component of the force and let it move in x direction, and we're going to do some more work, and that work is going to be equal to the x component of the force times that displacement right there along the x-axis. So to find the total work done, it's just the sum of those two. The work is just the x component of force times the x component of displacement plus the y component of force times the y component of displacement, and just add these quantities together. Notice that we end up with a scalar quantity. This way of combining force and distance is actually called the dot product. This is one of the ways that we can multiply vectors together. This is a very special type of multiplication. And just a couple of things to point out: when you take A dot B, you take the x component of A multiplied by the x component of B, add that to the y component of A times y of B, plus the z component of A times the z component of B. And this gives you a scalar quantity. All of the work and energy that we're dealing with is a scalar quantity. So this is the dot product, one of the ways to multiply vectors together. Now, one thing I want you to pay particular attention to is the sign of work. Work can be positive or negative. And so one thing you really want to know is that you understand how the direction of force and displacement relate to one another. So the work is equal to F dotted with delta R. So how does the direction of F and delta R relate when the work is positive? Think of it this way. If you've got an object moving in a certain direction and you want to speed it up, you want to increase the kinetic energy, which way would you push on it? Would you want to be pushing on it in the same direction it's moving, opposite the direction it's moving, or maybe perpendicular to the direction it's moving? Conversely, how would the direction of the force and displacement relate when the work is negative? Negative work means the kinetic energy is decreasing. How would you push on it in order to get it to decrease kinetic energy? That's what these two questions here are relating to. So make sure that you understand how these things are relating. Which way, if an object is moving to the right, would you have to push on it to increase kinetic energy? Remember from the previous lectures that the low speed approximation of kinetic energy is k is equal to 1/2 mv squared. So if you want to increase kinetic energy, you have to increase the velocity. If the object is moving left, which way do you have to push to decrease the kinetic energy? In other words, to lower the velocity, which way do you have to push on the object to get it to slow down? We'll be using these bar charts as a really handy visual reference for energy conservation. This is just the energy conservation equation that we wrote down before, K initial plus W equals K final. So what we do is if we have a certain amount of kinetic energy, we draw a bar chart that's proportional to the amount of kinetic energy, and then another bar representing how much work we have, and then we just add those two together. So all I've done is stack this block and this block on top of it to get the total amount of kinetic energy. So what we see is that when I have positive work, that's going to give me a lot more energy in the end. If I've got negative work, then I draw a bar below the line here, and this amount is how much we're going to have to chop off of this to get the final amount of kinetic energy. So I've got a lot of kinetic energy, I do negative work on the system, and I end up with a little bit of less kinetic energy in the end. So let's just kind of take a couple of examples and use the dot product. So let's say we've got an object moving to the right and you're pushing to the left. So for simplicity, let's just assume that the distance moved is 1 meter. So my delta R, let's see, assuming that positive x is to the right, my delta R is 1, 0, 0 meters. My F, for simplicity, we're just going to give it a magnitude of 1 Newton. So it's pushing to the left, that's the negative x direction, so -1, 0, 0 newtons. So the work done in this case is just F dot delta R is equal to -1, 0, 0, dotted into 1, 0, 0 Newton meters. So just remember that we multiply the components and then add them. So the work done is -1 times 1 is -1 Newton meters. 0 times 0 is 0 Newton meters. And then 0 times 0 is another 0 Newton meters. So the work done is -1 Newton meters. Newton meter is also called a joule. That's the unit of energy. So in the case that you are pushing to the left on an object moving to the right, negative work is done. And if we draw our bar chart, here is my K initial plus the work done is negative. That's going to be equal to my K final. So basically remove this amount from K initial and I end up with a lot less K final. All right, let's say that the object's moving to the left and you're pushing to the left. So my delta R in this case, let's just use the same magnitudes as before, only since it's to the left, it's going to be a -1, 0, 0 meter displacement. The force is the same as before, so it's still -1, 0, 0 newtons. The work done is newtons dotted into -1, 0, 0 meters. So -1 times -1 is 1. 0 times 0 is 0. 0 times 0 is 0. So we end up with 1 Newton meter or 1 joule of work. So we draw our energy bar charts, and assuming we've got some initial kinetic energy, and since I'm doing positive work, I draw my bar chart above the horizontal line, and And my kinetic final just comes from stacking these two on top of one another. So I get significantly more energy at the end.